Hello there, Mr. Sutton here, bringing you the AB Calculus 6-9 classwork solutions on accumulation. On this problem, we have the flow of oil through a pipeline given in this graph shown above, and this is the rate of change of barrels of oil, so barrels per hour, and they want to know which of the following best approximates the total number of barrels of oil passing through the pipeline that day. Well, this is the rate at which the barrels of oil is changing. So if I want the total barrels, I need to integrate this thing. I'm going to call this graph B of t, which is just the rate of change of barrels. I need the integral from 0 to 24 of B of t dt, which is to say I need the area under this curve. Now, I have no idea what this function actually looks like algebraically, so I'm going to have to estimate, because they did say approximate here. So let's see. I'll do this by counting squares. I've got 1, 2, 3, 4, and these are each kind of a half a square, so we'll count this as roughly 5 squares on this graph. Now, how much is each square worth in terms of area? One square is going to be worth 6 times 100, so roughly 600 barrels of oil per square. So 5 squares, 600 a square. 5 times 6 gives me 3,000 barrels, which is choice D. For this problem, I have a spherical tank with 81.637 gallons of water at time 0. For 6 minutes, water is flowing out with a rate given by this formula here, 9 sine of radical t plus 1. We want to know how many gallons of water are in the tank at the end of 6 minutes. So this is your basic FTC accumulation kind of problem with a little bit of a twist. So I'm going to first define a function w of t to represent my amount of water in the tank, just so I can talk about things a little bit more easily. So I can say that w of 6, which is what we're trying to find here, is going to equal my initial value, w of 0, 81.637. And then normally I would add the integral from 0 to 6 of my rate of change of w, which I'm going to call w prime, using this function here. There's just one twist on this problem. Water is flowing out, not in. So I actually have to subtract the integral of this, because this is negative water essentially. So since we're flowing out, I'm going to say minus the integral from 0 to 6 of w prime of t dt. And again, by w prime, I'm talking about this expression right here. So let me show you on my calculator what I'm doing here. So in my y equals, I'm going to put this 9 sine of radical t plus 1. And since it's a graphing calculator, I have to use x instead of t here. Let me quit out of that now. And let me do, let's see, 81.637, got to be precise here, minus math 9, so integral from 0 to 6 of, I stored this in y1, so alpha trace y1 and dx, and let's hope for the best. So that comes out to 36.606 if we round it off to the nearest thousandth of a gallon, and that ends up giving us choice A. Now, just as a little sanity check here, not for nothing, folks, but you started with 81 gallons of water. It flowed out for 6 minutes. So if you picked choice E, I mean, that, sanity check here, you should not end up with more water than you started if water is flowing out. So you could at least eliminate that one. For this problem, the rate at which motor oil is leaking from an automobile is modeled by this L function. And let's see here. We want to know how much oil leaks out of the automobile during the first half hour. So we've got to pay close attention here. They said that L of t is measured in liters per hour, and t is measured in hours. So first half hour, that means for hours we have to plug in 0.5. So we need an integral then of L of t dt from 0 to 0.5. And let's go ahead and plug that in the calculator. So I've got my L function plugged in as y1 in my y equals, and now I'm just doing math 9 integral from 0 to 1/2, so I'll just do 1 divided by 2, and that's going to be alpha trace y1 dx, and then all that comes out to about 0.541, and that's going to be in liters. So that's going to be, let's see, answer choice D. For this problem, during an evacuation drill, people leave a building at a rate of r of t, and we've got some values of r of t in this table here. So they want us to use a right Riemann sum with 3 subintervals in this table to approximate how many people leave the building in the first 15 minutes of the evacuation drill. All right, so we're essentially trying to find the integral of r of t from 0 to 15. And we can say that that is approximately equal to the following. So we wanted a right Riemann sum, they said. So we have a base of 5 and a height of 100. We're going to use this right 100 here, although it wouldn't matter on that first one. Next, we have a base of 5 again and a height of 75. That's the right endpoint of the rectangle. And finally, base of 5 times a height of 55. And now we have to add all this up without using a calculator. So a little trick you can use here. Since these are all being multiplied by 5, you could actually factor a 5 out of all of this and then do 100 plus 75 plus 55 inside the parentheses. So that would be 175 plus 55 would be 230. So if you factor out that 5 and then add inside, you're essentially doing 5 times 230, just to make your life a little easier here. So that's, let's see, 5 times 200 is 1,000. 5 times 30 is 150. 1,000, 150 would then be our answer, and that's, I guess, units of people if you care. So that's, but I mean, who doesn't care about people, right? So that would be choice B. For this problem, during a rainfall, the depth of water in a rain gauge increases at a rate modeled by this r of t function over here. And let's see, t is the hours since the rainfall started. We want to know how much did the depth of the water in the rain gauge increase from time 0 to time 3. So we have the rate at which the rain gauge is increasing. If we want to find out how much total it increased, we need to take the integral from 0 to 3 of this r of t function. And we're going to need the calculator for that. To make my life a little bit easier, I'm going to enter this crazy-looking function in my y equals here. And now let me just take the integral of that from 0 to 3. So math 9, integral 0 to 3. And then I'm going to do alpha trace y1 dx. And that all comes out to roughly 5.401. And that's in centimeters. So that ends up giving us choice D. On this problem, the number of insects in a population is modeled with a function whose first derivative is given by this p prime function here. And at time 0, we're told the number of insects is 40. So we want to know which of these statements is true. So at time 0, number of insects is 2840. Or at time 10, rather. At time 10, number of insects is increasing at a rate of 360. At time 10, the rate of change is increasing at a rate of 18 insects per day. So this is talking about values of p of 10, p prime of 10, and p double prime of 10. So let's actually put this on our calculator in order to figure out all of these different things. So I've entered this on my calculator now, so I can use p prime whenever I want. Now, for the first part, we have to figure out p of 10. That's going to require the FTC. We're going to have to do the initial value at 0, which is 40, plus the integral from 10, or actually from 0 to 10, of p prime of t dt. And for that, I'm going to use the calculator. So let's see, quitting out of there, I've got 40 plus math 9, integral 0 to 10. And now I stored p prime as my y1, so I'm going to do alpha trace y1 dx. And all of this comes out apparently to 2840. Well, that's a nice round number. Okay, so statement 1 then is actually true. For statement 2, now we're asking about p prime of 10, and they're claiming that p prime of 10, the rate of change, is positive 360. So let's actually plug in 10 to p prime and see what we get. So again, p prime is just my y1 that I've entered in my calculator. So I'm going to go to alpha trace y1 and just open up parentheses and plug 10 in here. And that comes out to 360. So statement 2 also happens to be true. Now, just looking at my options here, they had 4 answer choices. A, B, and C all were singletons, right? These are all claiming only one of these things was true. Well, now that I've determined that 1 and 2 are both true, there's only one of these answer choices that makes sense, and that would be choice D, where they say that all 3 of them are true. There's no option for just 1 and 2. But if there's doubt, we can actually figure out if statement 3 is true or not. So statement 3 is talking about p double prime of 10, and they're saying that that's 18. Well, to do that on my calculator, I'm now going to go to math 8 and do my derivative here with dx, and I'm taking the derivative now of alpha trace y1. Where am I doing it? At x equals 10. And that comes out to, 18. Big surprise there, right? So that also turns out to be true, but now we've proven it. We feel so much better, and we can pick choice D. For this problem, we have a basic setup here with the rate of fuel consumption in gallons per minute of an airplane being recorded in these graphs and tables up here. And we're told that this function that we're showing up here is twice differentiable and strictly increasing, which might help us out a little bit later. So first thing they need us to do is, using the data from the table, approximate r prime of 45. Well, since we don't know the algebraic formula for the r function, we're going to have to approximate IROC using an AROC from this table. So you just have to find AROC for r on any interval that contains 45 for the time. I'm going to go with the interval from 40 to 50 because that's the smallest interval. So my AROC then is going to be r of 50 minus r of 40 over 50 minus 40. So that's 55 minus 40 over 50 minus 40. 15 over 10, we could reduce that to 3/2 if we wanted to. And what's our units of measure going to be? Well, since it was gallons per minute, and this is now the average rate of change of gallons per minute, every time you take the derivative, you tack on, or you divide by another time unit down here. So this is going to be gallons per minute, or gallons per minute squared. So 1.5 or 3/2 gallons per minute squared. On this problem, the rate of fuel consumption they're telling us is increasing fastest at time 45 minutes. Based off of that, what's the value of r double prime of 45? Okay, so we barely have information about r of t. R prime of t we had to estimate using AROC on the last problem. Now they're asking about r double prime of some value. So there's definitely some kind of special case going on here. We have to do a little bit of decoding on this one. They're telling us our rate of fuel consumption, namely r, is increasing fastest at 45 minutes. Well, what does it mean if it's increasing fastest? That means that its derivative, r prime, reaches a max value at 45 minutes. So in general, if r is increasing fastest at 45 minutes, r prime has a max at 45 minutes. Well, what does that mean about r double prime? Since 45 is not an endpoint, that means this max can only be caused by some kind of critical value for r double prime. So that means r double prime has got to be either 0 or does not exist at time 45. Well, can we rule out either of these possibilities? The key at this point in the problem is reading the problem again and saying that, they tell us that this function r of t is twice differentiable. Well, what does that mean if r is twice differentiable? Well, it means that you can take the derivative of r everywhere, so r prime exists everywhere. It also means that the derivative of r prime, namely r double prime, must exist everywhere. If I can take the derivative everywhere of r prime, that means r double prime is defined for all values. So that means that r double prime can't be dne. It's got to be 0 because it's defined everywhere. So for that reason, r double prime of 45 is 0. On this part of the problem, they want us to approximate the integral from 0 to 90 of r of t dt using LRAM on this table, and they're saying, hey, yeah, use 5 subintervals. All right, so let's do this part of the problem. Then there's another part after that, but we'll get there when we get there. So I can say that this integral is approximately equal to the following. I'm using LRAM, so I've got a base, this is the bases over here, the base of 30 times a height of 20. I have to use the left endpoint of each rectangle. So 20 is the left endpoint of my first rectangle. So 30 times 20 plus a base of 10 now to go from 30 to 40 times a height of 30. This is our left endpoint between 30 and 40. Plus a base of 10 again, height of 40. Plus a base of 20 from 50 to 70, height of 55. And then finally we have a base of 20 times a height of 65. Now, at this point, once you've written out all these constants, you could actually stick the units on the end, that units being gallons, because we just integrated gallons per minute, and call it a day, and then answer this next part of the problem. But in the next part of the problem, they're asking if our approximation is less than the value of the true integral. So it would be convenient if we had an actual number to say this number is less than or greater than this true value. So I'm going to do all this on the calculator. This was actually a calculator question. So plugging all that in the calculator gives me an end result of 3,700 gallons. And is this over or under? Well, the key on this is seeing that this is LRAM and also seeing that our function is strictly increasing. If our function is strictly increasing on the interval from 0 to 9, you do have to mention this interval in here to get credit. That means that LRAM is going to under-approximate. And if you look at here, if you're doing the left rectangles, left endpoint of the rectangle, you're always ending up underneath this curve, so you're going to have less than the true value. So I'm going to write this just by saying 3,700 is less than this integral of r of t dt from 0 to 90. For this last part of the problem, we're given that, b is between 0 and 90, and b could actually be exactly 90. Given this, they want us to explain the meaning of integral from 0 to b of r of t dt, and also 1 over b times the integral from 0 to b r of t dt in terms of fuel consumption. Indicate units of measure in both answers. All right, so if I'm taking this integral, this is kind of what we did in an earlier part of the problem. You essentially were finding the total amount of fuel consumed, and this is going to be in gallons, from time 0 to time b. So you need all of this, the what, the units, and also the when. Moving on down to this one now. This one's almost the same thing, except we're dividing by, this is essentially 1 over b minus 0. This is the interval length. If you're dividing by the interval length, you're actually finding the average for whatever it was that you were integrating here. Since the thing we are integrating is the rate of fuel consumption, this is giving us the average rate of fuel consumption. And this is now going to be in gallons per minute. It's going to have the same units as the original, r of t. So in gallons per minute from 0 to b minutes. On this problem, my basic setup is I have hot water dripping through a coffee maker, filling a large cup with coffee. Coffee. The amount of coffee in the cup at time t is given by some differentiable c function whose selected values are given in the table here. So this is the amount of coffee in your cup at different times from this coffee maker. Part A, using the data in our table, we want to approximate c prime of 3.5. Since I'm approximating an IROC and all I have to go on is a table, I'm going to have to take the average rate of change of this c function on some interval that contains 3.5. Probably the best interval would be the interval from 3 to 4. So I'm going to do AROC is going to be c of 4 minus c of 3 over 4 minus 3. And actually plugging in numbers here, notice I wrote approximately equals because I don't know the exact value of c prime. So that's going to be then 12.8 minus 11.2 over 4 minus 3, which is just 1 there. So this is just going to be, 1.6 if we need to. And that's going to be ounces per minute because my original units was ounces, and I'm finding the rate of change of that with respect to time, so that's ounces per minute. On this next part of the problem, they want to know if there's a time at which c prime has to equal 2. So one way that you could go about this is using the mean value theorem. If you're trying to guarantee the derivative of some function is a certain value, and all you have to work with are values of the original function, using the average rate of change to pinpoint the instantaneous rate of change is a good way to go. But before we can use the mean value theorem, let's establish the preconditions. This will only work if our function is differentiable on the interval from 2 to 4. Looking back at the problem here, they're telling us that we have a differentiable function c, so they did spell out that it's differentiable. Since c is differentiable, our mean value theorem applies. So let's go ahead then and find the other condition of the mean value theorem, which is showing that we have an average rate of change on the interval from 2 to 4 with a value of 2. So average rate of change, that's going to be C of 4 minus C of 2 over 4 minus 2. So that's going to be 12.8 minus 8.8 over 4 minus 2. You could certainly have worse numbers to work with here. This is really 4 over 2, which we will simplify to 2. So by the mean value theorem, there is going to be a time then on the interval, the open interval from 2 to 4, for which C prime of t takes on a value of 2. For this next problem, they want us to use a midpoint sum with 3 subintervals to approximate the value of 1/6 integral from 0 to 6 of C of t dt. All right, well, let's go ahead and do that, and then we'll figure out the rest of this. So I've got this thing is going to be approximately equal to 1/6, and I wrote approximately equal because they said approximate. So now I launch into my midpoint Riemann sum. So my 3 subintervals, we've got 0 to 2, 2 to 4, and 4 to 6. Dealing with our first rectangle from 0 to 2, I've got a base of 2 times a height of 5.3, because we have to use the midpoint output value. Next, I've got another base of 2 and a height of 11.2. We have to use the 3 value there. And then finally, base of 2 times a height of 13.8. And let me go ahead and simplify all this. I don't have to simplify it. I at least have to put units on it, though. If you were just dealing with units, then this units would be the ounces of coffee. We'll talk about why that is in just a sec, though. But if you wanted to, we could go ahead and simplify this. So to make this a little bit easier, because this was a no calculator problem, I factored a 2 out of this parentheses. So I essentially had 2 over 6 times all these decimals added together. So that was 1/3 times, let's see, what's 5.3, 11.2, and 13.8? Well, I'm going to add these strategically. 11.2 and 13.8. Let's see, that means we've got essentially 11 plus 14, which is 25, plus another 5.3 is 30.5, or 30.3 rather. 1/3 of that, just dividing this by 3, that's 10.1. And so using correct units now, they want us to explain the meaning of this in the context of the problem. So what we just found here, this 10.1, this is going to be the average amount of coffee in our cup, because this 1/6, this is really like 1 over 6 minus 0, 1 over b minus a. This is an average value situation. So this is the average amount of coffee in the cup, and our units is just going to be ounces of coffee. It's the original units, and this is going to be from times 0 to 6 minutes. For this last part of the problem, amount of coffee in the cup in ounces is modeled by this B of t formula here. Using this model, we want to find the rate at which the amount of coffee in the cup is changing when t equals 5. Okay, so for this, we need to figure out b prime of t. And again, this is a no calculator question, so you couldn't just plug this in your calculator and plug 5 into its derivative. So our derivative, this 16 gets differentiated away, and this is going to be negative 16e to the negative 0.4t times a tail of negative 0.4. So let's see, negative 0.4 times negative 16, that's going to be a positive. It's going to be positive 6.4, I believe. So positive 6.4 e to the negative 0.4t. There we go. And so that was the most painful part of this problem. After that, we have to plug 5 into this. So here we go, plug in 5 for t. And you might be saying, oh, this is so unfair. I don't have my calculator. How can I possibly figure out what this comes out to? But here's the good news. On a free response, as long as you have all constants, you're actually done. The only thing you have to do on this problem is also throw in the units. Now, you could, if you wanted to, simplify this a little bit. I mean, this is going to be negative 2, so e to the negative 2 up here. But at the end of the day, you just have to put on the units, which in this one, since we just took the derivative of amount of coffee in the cup, the derivative of that is going to be ounces per minute. So 6.4 e to the negative 2 ounces per minute.